This presentation is going to be about motion graphs for motion in one dimension, but you could also call it an introduction to calculus. What we're going to be looking at is how the graphs of motion can help us understand how an object is moving, how it can be related to the equations of motion, and how we can take motion that we understand and create graphs of it. The essential idea that this is all related to is that motion can be described and analyzed by the use of graphs and equations. And mostly we're going to be focusing on the graphs piece of it. And at the end of the lesson, you should be able to sketch and interpret motion graphs. Specifically, we are going to be looking at the slope of the position versus time and velocity versus time graphs. We'll be looking at the area under the curve for velocity versus time and acceleration versus time. We'll be looking at the graphs of position versus time and using those to construct the velocity versus time graph, and vice versa, using the velocity versus time to construct position versus time. And finally, and what I think is a really fun one, is we're going to be relating the velocity versus time graph for constant acceleration to create those big four equations of motion that we use when we're doing algebraic approaches to analyzing motion. I think that's really fun. And along the way, there'll be some exercises for you to practice these things. First, let's think about one-dimensional motion. Have just a picture in mind of what's happening. I like to imagine a car that's accelerating along a road. And when we think about that, we know we're going to describe the motion of objects in terms of the position of the object, the velocity of the object, and the acceleration of the object. And we can graph those quantities. So we can think about a position versus time graph, a velocity versus time graph, and whoops, can't quite see the title, acceleration versus time graph. But more importantly, and that's what we're going to focus on today, these quantities are related to each other, and they can be determined from one another. When we think about the relationship between position and velocity, we know that velocity is the rate of change of position with respect to time. And so the graph of velocity is going to be related to the way that the position graph changes. The same thing is true with acceleration. Acceleration is the change in velocity with respect to time. And so we'll be looking at the way that the velocity graph changes to construct the acceleration versus time graph. In terms of calculus, this is known as the derivative. We're taking the derivative of the position with respect to time to find the velocity, and the derivative of the velocity with respect to time to find the acceleration. You can look at this the other way as well. We know that acceleration changes velocity. When you have a constant acceleration, we know that the change in velocity will be equal to the acceleration times the time that elapses. And the position is changed by the velocity. So for a constant velocity, the change in position is the velocity times the time that elapses. It's a little bit more sophisticated than these equations are shown right here, but this is related to the calculus of integrals. When we look at the graphs, these calculus topics become a little bit easier to think about. We're going to look specifically at position and velocity versus time and how they're related. For the derivative, the gradient of a graph shows how the quantity is changing. What we mean is that if we look at the slope or the gradient of this line at any point, we can see how that quantity is changing, whether it's approximately staying the same, increasing, changing from increasing to decreasing, or decreasing. On the other hand, if we look at the integral, we're looking at the area underneath the curve. And by that I mean, what is the region that sits between the graph and the axis? If that's above the x-axis or the time axis, you have a positive area. And if it's below the axis, we have a negative area. And that's going to show how the quantity accumulates with respect to time. Let's look at some specific examples. Right here in the beginning of the motion, the position versus time graph is roughly constant. It's horizontal. What that means is that the position is staying the same for that time. And sure enough, if you look at that, the way that that's changing, that's the velocity, and the velocity in that region is 0. it's not moving, right? So the slope of the graph, the gradient of the graph is 0, so the velocity will be 0. Moving over a little bit, we have a region where the position versus time is increasing. And so here we expect a positive gradient, meaning a positive velocity. The gradient is approximately constant, so the velocity is approximately constant. So that's the way that the gradient of the position versus time graph relates to the value of the velocity versus time graph. Let's take a step back. Let's look at what happens with the area under the curve. This is showing how the velocity accumulates change for position. So here at the beginning of the graph, the velocity is 0. There is no area under the curve, unless you count that tiny little bit right there. So we see with the position versus time graph that it's not changing. There is no change in position because there is no area under the curve here. Moving to the region where the position is increasing, we see that there is area between the velocity curve and the axis. It's positive area, and so we expect to see the position change. And sure enough, up here we do. So just to cover that again, the rate of change of the position versus time graph, the gradient, tells us what the value of the velocity is, and the area under the curve tells us what the increase is in position. Let's look at two more regions to understand this a little bit better. Over here at the end, the position versus time graph has a steep negative slope, steep negative gradient. And sure enough, the velocity has a large negative value. Thinking about it in terms of integrals, we have the area under the velocity curve is large and negative, and so we see a large decrease in the position versus time graph. Near this maximum here on position versus time, we see the gradient changes from positive, sloping upwards, to negative, sloping downwards, and right in the middle, of course, it's horizontal, it's 0. Looking at the velocity, we see in that same region a positive value, followed by 0, followed by a negative value. So this peak here at the top is associated with a positive, 0, then negative value for velocity. Thinking about it in terms of integrals and areas, if you look at the area under the velocity curve, we see that there's a small positive area followed by a small negative area, suggesting that we have a small increase followed by a small decrease in the position graph. So just to check yourself, see what connections you see in this collection of graphs. I've expanded it so that you also see an acceleration versus time graph, the velocity versus time graph, and the position versus time graph. These are all lined up and their time axes are the same, so you might identify some different regions and see how you can relate the area under the curve of the velocity graph to the change in the distance, or for example, the slope of the velocity versus time graph to the value of the acceleration. So go ahead and pause the video for a couple of minutes and see how many different connections you can make between these graphs. Okay, welcome back. It's possible that you found half a dozen or so different connections, which is great. It's also possible that you weren't really sure what to do. So let me give you a few hints about things that you could look at. So when you're looking at this, think about which graphs make it easy for you to identify the changes in motion. So if it's more comfortable for you to think about distance versus time, think about one specific graph in one specific region, and then try to understand that in terms of the velocity. For example, here between, like, say 27 and 30 seconds, what's happening on the distance graph, and compare that to what's happening on the velocity graph. Another thing you can do is you can try picking a specific time and looking at all of the graphs to describe what's happening. At 15 seconds, we're at a specific distance. The velocity is 0, but the acceleration is large and negative. What does that mean about what's happening? And finally, if you found all these different things and now you wanted something more to think about, something a little bit harder, try to think about what would happen if the acceleration versus time graph had a slope to it. because that can give you some very interesting things to think about. Take another couple of minutes, think through these graphs a little bit more, and then we'll move forward. Okay, now for part two. What we're going to look at here is how to derive the kinematic equations of motion for uniform acceleration. And the place we're going to start is we're going to start here with the velocity versus time graph. And so let's just carefully look over what we've learned. The acceleration is understood to be the slope of the line. And since we're looking at uniform acceleration, the slope of this line, the gradient of this line, is constant. The area under the curve is interpreted as the change in the position of our object. And that is obviously a shape that we can compute the area for. Let's start putting some values onto this curve. To start with, let's look at time 0. So this is where the part of the motion that we're interested in is starting. And we'll call this t is equal to 0. We'll call the initial position x0, and we'll call the initial velocity u. So these are the initial conditions for the motion, and then from there, acceleration will take place, and we'll reach the end at time t, and we'll have a velocity v at that point, which will be larger than u, and we'll be at a new position x of t. So we'll use that function notation to describe that second position. So let's start by looking at the easiest part. Let's look at the gradient. We know that the acceleration is defined as the rate of change with respect velocity with respect to time. And so here we look at the change in velocity. So velocity goes from u to v over the change in time, which is the time t here, because we start at 0 and we end at t. So our change is v minus u, and the change in time is t. Rearranging this is fairly easy. We'll multiply both sides by t, move u over to the other side, and we get our first equation of motion, that the final velocity is the initial velocity plus the acceleration times time. Pretty straightforward, pretty easy there from the gradient of the line. Taking a look at the area now, we're going to break this area up into two pieces. So there's this sort of rectangular area, and then there's this triangular area. So the total area under the curve, which is going to be related to the change in x, that's going to be the rectangle's area plus the triangle's area. Little basic geometry, right? We know that the area of a rectangle is the height times the base, and the area of a triangle is half the height times the base. So starting to substitute things in here, this is going to be a little bit tricky to look at. So the area, remember, is the rate, or is the change in the position. So the change in the position, we've defined the final to be x of t minus x0, also known as the displacement. The area of the rectangle, the height of this on the velocity versus time graph, is u, the initial velocity, and the base is t, the time. So we have height times base is u times t. For the triangle, the height is the difference between the final velocity v and the initial velocity u. That's this height here. So we have half v minus u, and the same base as we had for the rectangle, so times t. Little bit of rearranging, and we end up with the displacement s in our IV notation. The final position minus the initial position is equal to u times t plus 1/2 a t squared. Where did this a come from? Why is t squared? Well, let's take a look up here, and from this expression at the top for acceleration, we know that v minus u over t is equal to a, so v minus u is equal to a times t. So we make that substitution here, and we have 1/2 at times t, which is 1/2 at squared. So we picked up our two of our equations for uniform acceleration just by looking at the gradient and the area under the curve. Pretty cool, right? This is also something that you could do with calculus from these definitions. Here's a follow-up that I want you to pause and think about and see what you can do. What would happen if instead of treating this area as a rectangle plus a triangle, we treated it as a trapezoid? You can see here that we have two parallel sides, and then we have height or a base length for the trapezoid. So go ahead, take a few minutes. Maybe you need to Google it. What's the area of a trapezoid, and what do you get when you use the values on the graph to compute that area? Okay, I hope you did take a look at doing that. It turns out that if you treat this as a trapezoid, you have 1/2, or the average of the two bases times the height. In this case, the trapezoid's sort of on its side, so it's a little bit strange. The height is actually t. This is the altitude of our trapezoid. And then the average of the two bases, we have one base is u, one base is v, so we have v plus u over 2 times t. And this is, of course, our expression for the displacement when you have an initial and final velocity. You take the average of the initial and final velocity, multiply it by the time. Of course, this only works for uniform acceleration, but that's the case that we have here. So that's great. Now, there's one more equation of motion. So I'm going to give myself a little bit more space. We know that we got this from the gradient. We got these from the area. And now what I'm going to do is I'm going to work on putting these two together. So v is equal to u plus at, the expression we got from the gradient. We're going to take that and we're going to square it. So we'll square the left-hand side and we get v squared. And squaring the right-hand side, u plus at squared. Expanding that is a little bit ugly. Yep, what we're going to end up with, obviously u squared, and the last term a squared t squared. And then the cross term, 2 times u times a times t. Now, this doesn't look familiar at all, but if we pull out 2 times a, it's a little bit strange because 2 is not a common factor here, but follow along. We pull out 2 times a, so we're left with ut for this second term, and we're left with 1/2 at squared. And that 1/2 at squared hopefully triggers a little bit of a little wisp of a memory that you remember back here. Ut plus 1/2 at squared, that's just the displacement. And so making a substitution here of the left-hand side of this expression from the area into the right-hand side, and we end up with v squared is equal to u squared plus 2as. So this is a really, really great way of showing how just from this very simple graph, a line with a starting velocity and an ending velocity, by using the gradient and using the area, we can come up with the big four equations of motion that we use to work on kinematic problems when we're looking at them algebraically instead of looking at them graphically. So at this point, we've covered all of the things. I want to leave you with 2 activities, and I'll leave you some time to pause and work on them. First, we have an exercise where we have a velocity versus time graph. This time, instead of looking at that in terms of variables, coefficients, this one is very nicely labeled up with values for the velocity in meters per second, values for the time in seconds, broken down into 4 regions of motion, A, B, C, and D. And the question for you is to spend some time on, can you describe this motion? And not just describing the motion in terms of velocity, but can you describe it in terms of how the position is changing? Can you describe it in terms of any acceleration? And then take this graph and construct the position versus time graph and the acceleration versus time graph, so that you end up with something that looks like what we looked at back here in slide 6, where you have the distance, velocity, and acceleration. So you have this graph here. Find the acceleration, find the distance. Just a quick reminder, right? Acceleration we're going to find by looking at the slope of the velocity, and distance we're going to find by adding up the areas under the curve. So I'm going to have you pause this video and take some time and sort this out. Really? You actually did that? You didn't just let the video keep playing? Okay. All right. Second exercise to take a look at to make sure that you're feeling good about this is called running errands. And what I want you to think about is describe in words a description of you running errands along the spine of the school. The spine of the school is important because you want to be thinking about this in one dimension. You know, are you visiting the library, the administrative offices, the school store? What are you doing along the spine? So think about going back and forth. What offices will you visit? What are you going to do there? Then construct the graphs of your motion along the hallway. So what will your position versus time look like, your velocity versus time, and your acceleration versus time? Estimate those distances and times so that you can scale your graphs correctly. The time axis should be the same for all of them. And then do what you can to make your graphs quantitatively consistent, so that if you take a certain amount of time to cover a certain amount of distance along the hallway, your velocity is numerically accurate. This is going to be a challenge, but it will give you a really good sense of how well you understand this material. So go ahead and pause for 5–10 minutes and work on that. Okay, excellent. Please share your graphs with me so that I can take a look at those and help you think through any changes that need to be made, or just congratulate you on getting all of your errands done. That's the end for this presentation. Just to summarize, we've been looking at how motion can be described and analyzed in terms of graphs and equations. The big takeaways have been how to interpret the slope of position versus time and velocity versus time graphs, and how to also use the area under the curve to interpret velocity and acceleration graphs. We've connected the velocity graph to acceleration versus time and position versus time, and position versus time to velocity versus time, vice versa. And my favorite part, we've related the velocity versus time graph for constant acceleration to the big four equations of motion. Hope you enjoyed that. Talk to you again soon.